Moment of inertia, not particularly important for this particular problem because alpha is 0, because it's in rotational equilibrium.
Sorry, what was it? What does it stand for?
I is called, this is the moment of inertia. Inertia is the property of an object that gives it the tendency to want to keep doing whatever it's doing, to travel at a constant velocity. Rotational inertia or moment of inertia is the tendency of an object to want to keep rotating at a constant angular velocity.
And then the alpha?
Angular acceleration. I did use another term here for moment of inertia. I also called it rotational inertia. Some textbooks call it rotational inertia. That seems to be something that's sort of shown up in the last 20 years. Moment of inertia is the usual term. The term moment, if you ever see the word moment, not as in part of momentum, but moment, like moment arm, moment of inertia, the second moment is not the third axis. Moment generally deals with things that are rotating. All right, so torque. We know that torque is R cross F. Forces, I got 3 of them over there. R depends upon where the pivot point is, or the axis of rotation. So what is the axis of rotation of a beam that's just sitting there? That's what you mean by that.
0.
Where is 0?
The axis, and the axis?
In the center?
So, here? I wasn't sure if that's what you meant, Dylan, but someone suggested that. Why not here?
I guess it could be there too.
Well, it could be. For something, if there's a natural axis of rotation, like on a door, there's hinges. That seems natural. That is actually the best place to pick it. On something like this, it's not moving at all. There is no natural pivot point. If I snip this wire, it's not like it's going to rotate about this spot. If I snip that wire, what's the rotation point going to be? So it's not obvious necessarily what the rotation point is. So you can pick any place you want. Middle is absolutely fine. Let's do the middle, and then we'll pick another spot. So we pick the middle. So I got R1 cross F1 plus R2 cross F2 plus I'll just call it RW cross W. Oh, I guess FT1 and FT2 is equal to 0. We're now left with another situation though. What is the direction of the torque from the tension 1? If the middle is our axis, the middle is the axis of rotation. If that's the axis of rotation, which way is this trying to rotate it?
Wait, are you talking about like if you cut it?
No, not if you cut it. If that's my pivot point right there,
right,
which way is this trying to spin it?
Clockwise.
Into the board.
Yeah, clockwise.
Okay, yeah.
But the thumb goes in.
Yeah.
I'm trying to get you away from clockwise, counterclockwise. It's bad news. Nothing but trouble. If this is my pivot point here, because someone said so, which way is this trying to spin it?
Away from the board?
Pardon?
Away from the board?
Away from the board, that way. So, your thumb, you said it correctly, but your thumb was not necessarily pointing the way that I would have expected.
Yeah.
So it's trying to rotate, this is trying to rotate it like that, this is trying to rotate it like that. So it's out of the board positive or into the board positive?
Whichever one you make it,
Yes. Which one do you want to make it?
into the board.
Okay. So R1 cross FT1 is positive. My tension is perpendicular to R. Again, R is going that way. There's my R1. So I just multiply them. So it's positive R1 FT1 plus, well, the next term, what would it be?
Negative. Is it negative FT2 as well, or is it just, okay.
It just,
Just
the negative sign, we got the negative sign right there. There's ways of dealing with it. Yeah, there are other ways of coming out with a negative sign, but we already thought through, we know it's going to be in the negative direction, so it's just going to be the product of the magnitudes there. Plus the weight. Which way is the weight trying to spin it?
Straight down.
What does spinning it straight down mean?
I don't.
Would it be zero?
Is it trying to spin?
It would be zero. It's not trying to spin it. From a math point of view, R is a vector from the axis of rotation to where the force is applied. What is the distance from the axis of rotation to where the weight is applied? Or what's the magnitude of that moment vector? Moment arm vector.
Say that again.
R is a unit, keep messing up there. R is a vector, it's the moment arm. It's a vector from the axis of rotation to where the force is applied. What is, so my axis of rotation is right there. What is the magnitude of the radial vector of the moment arm? What's the magnitude of the moment arm from the axis of rotation to where the weight is applied?
0, because the weight is applied in the middle, in the center of the mass.
So it's 0 if we can think through it and say, well, the weight's not trying to spin it around itself. Or the radial, the moment arm is 0. So basically, it drops out.
Okay.
So is that because it's equidistant from the center, the tension?
Oh, those are equal.
It is 0 because the axis of rotation was chosen to be where the weight is.
Okay.
If the weight had been not at the center, and you said, oh, let's put the axis of rotation at the center, then it would apply some torque.
Okay.
Typically, when you're doing this, when you pick at the axis for something where it's not obvious, you pick at some place that's going to eliminate a term. So by picking it here, here, or here, we would have eliminated one of the torques. This is not necessarily, the weight is not necessarily the simplest way, but perfectly fine. So we're still trying to find FT1 and FT2. So what is R1?
1.5 meters?
Well, that's, is that from the
Or
edge?
would it be 10 minus 1 point?
It would be neither. Somebody say it?
3.5 meters?
Yes, 3.5 meters. It's from the axis of rotation to here. The whole thing is 10 meters, so this would be 5 meters here. And that's 1.5, so it's the difference.
Okay. Okay. That makes sense.
R2,
That'd be, yeah, 2.9.
yeah. So what I have here is now a set of math equations that I hope everyone can solve, barring Carol's heresy. So we have 3.5 times ft1 minus 2.9 times ft2 equals 0. And from over there, we have ft1 plus ft2 is equal to 190. Two equations, two unknowns. At this point, there's probably 10 different ways of solving it, at least. I don't know what your personal preference is. I am just going to multiply that bottom equation by 2.9. So my second equation is 2.9 ft1 plus 2.9 ft2 is equal to whatever that is. There's a 0 there.
So what happened to the 3.5? I'm sorry, we're not.
What happened to the what?
To the 3, yeah.
We'll bring that back in just a second.
Okay, so we're just working one.
So just manipulating the second equation for now.
All right.
2.9 is 190.
551.
Now I bring in the second equation, I just write right next to it, ft1 minus 2.9 ft2 is equal to 0. I add the two equations together. My ft2 terms cancel out, and I'm left with 6.4 ft1 equals 551. Somewhere around 90, just shy. 89. What is it again? 86.
0.09.
Units? What did we find?
Tension.
Which has units of?
Is it newtons?
Say it like you mean it.
Newtons.
Yes. Newtons. Now we find ft2. Well, I know ft1 and ft2 add up to 190. So using what's the purple equation right there, ft2 is 190 minus 86.09. 103.91 newtons. Assuming it didn't make a careless error there. Let's see if this makes any sense at all. I have these two wires holding this beam up. Which wire is closer to the center?
The right wire.
All right, so the second wire. So I would expect the second wire to have a greater force on it, and it does. So at least in that respect, it makes sense. At this point, let's take a small little break. I know we've got only 20 minutes left, so let's not go too long, but if you need to stretch your legs, get a drink of water. to smoke. You probably don't have time to go down through that. And you shouldn't be smoking anyway. All right. We're rolling. And part of Daniel's hat will be more like. All right, I'm skipping a bunch of chapters right now, hitting this question of, with limited time, what do you include and not include? I was going to skip over the torque. Basasan did make a good point about that torque is something for those who end up doing physical therapy, which I think there's a number of you. Torque is something that you will see again as part of that. And then as far as preparing for 152, we'll need to talk a little bit about vibrations and waves. So let's talk about vibrations and waves. So let's start out with everyone's favorite. Sorry, second favorite. Everyone's favorite is a graph. Let's start out with the second favorite, vocabulary. Amplitude, period, frequency, wavelength. There's a fourth one in there that I'm blanking on right now. Oh, angular frequency. So we're talking about any type of, this is repetitive motion. And in case you can't read it, the word is repetitive.
Oh, yeah, okay. I was going to say all of those are, yeah.
And so when you're expressing, when you're writing down something that is repetitive motion, there are various ways of describing it. Probably the simplest is if I've just got a wave that's oscillating back and forth. This could represent lots of different types of wave, but there's some middle point. And the amplitude is just, I'm going to say distance, but let's put that in quotation marks. It's not necessarily a distance, it depends upon the context, but from here to here, whatever that distance is or that change difference in pressure is, it's the difference of whatever this is measuring from the peak to the middle or middle to the trough. This is the amplitude. Peak to median, or median to trough, or half peak to trough. And the reason why it's sort of nebulous, if we were talking about a physical slinky, I had a really long coil that I was just vibrating up and down, or battle ropes for those who worked in the gym on battle ropes. We've got these ropes and you're going up and down like this. This would physically represent a side view of the wave. Although for battle ropes it probably tapers off, but let's assume that you're powerful enough that, and you've got ideal perfect rope there, that you can create this wave pattern like that. If this is sound, this would represent high pressure and low pressure. In other words, a high concentration of particles in the air, low concentration of particles in the air. And so this would be from the ambient pressure of air to the peak, or ambient pressure to the lowest. Probably more accurately, if I wanted to represent air, if this were sound, for example, and so this is being modulated by air pressure, this would be a whole lot of molecules in the air. You know, generally referred to as air molecules, even though I know that there's no really such thing as an air molecule. this is a high concentration, and then you've got not many right here, and then you've got a high concentration again, and then it tapers off, and then you got a high concentration again. It's just that this representation is kind of difficult to write. So we typically write it this way. I could also represent this by just the peaks. So if you think about a stone being thrown into a pond, a still pond, and you get that ripple going out. So you can also write it like we've got a series of ripples here. And this is generally the peaks. So the trough would be roughly halfway in between. The symbol used for amplitude, if I was just doing it generically, I'd use a capital A, but it really depends on what we're talking about. If this is pressure, I'd probably use a capital P. If this were an actual physical distance, then I would use X or something like that. Period, symbol for period, is a capital T. For those who have used capital T for tension, now's the time to change that. This is the time to produce one cycle of repetitive motion. The period of the Earth's rotation about the sun, revolution about the sun, is 1 year. The period of the Earth spinning is 1 day. The period of the moon going around the Earth is about 28 days. Frequency, F. How often repetitive motion occurs. In that sense, just like in English, it's how frequently something happens. And that's often, not often.
And it's a cursive looking F.
Yeah, the same F I used for friction.
Okay.
We call it the Baroque F.
Baroque.
I don't know if anyone else calls it that, but that's what I call it. Wavelength. This is